So I'm about kind of old style, old school conformal bootstrap, and also I hope there are still something interesting in it. Okay. It's probably not necessary. Okay, 2-point function and 3-point functions are fixed by conformal symmetry, and you have some. You can do conformal block decomposition by using OPE, and then you have some structure of. Yeah, let's skip this. Okay, that's. Yeah, this is a Gaussian equation and how to acting on it because I was given this talk to some other people. But yes, okay, let's start with here. This is the first, a very interesting result first obtained by these groups. And well, of course, there's the famous Eisen Island, but actually this CFT, this plot contains more information than just this island, this kink. And actually later, Nakayama and Otsuki, they realize actually if you draw a line on 3, a straight line on 3, and intersect with this curve, okay. Well, yes, you are consider this is the plot that you get from considering single correlators, sigma, 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 sigma. Yeah, but actually it doesn't matter. You can also think about it as epsilon, 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 and you allow epsilon to appear in its OPE, and you realize this curve doesn't change as you do that, okay? So then you can interpret this guy as epsilon, and you draw this line, and there's a lower bound for epsilon. If this simply tells us that for any second-order phase transition, which could not be reached without fine-tuning, the CFT needs to contain an operator whose dimension is bigger than 1.04. Because I mean, if your theory contains two relevant neutral scalars, that is neutral in any Fourier symmetry, suppose you set up the system on a lattice or whatever, you need to do fine-tuning. You can just think about what's the difference between Eisen model and tree-critical Eisen model, right? So this put a constraint on the scaling dimension of epsilon operator, and actually this works for any CFT, okay? And in terms of critical exponents, it tells you that mu needs to be bigger than a certain numerical value. No Z2 symmetry is assumed. Any symmetry, any 04, 05, because they always have a singlet operator. Think about it when you are doing lattice simulation, and that operator that is invariant under ON symmetry would always be the temperature that you are tuning. Or, yeah, this is not my work, but yeah, this is 3 dimensions. You can do other things in 2D if you want, but yeah. So. Yes, I mean, okay. The assumption is that I want to reach the second-order phase transition without fine-tuning. So that's basically, yeah, that just means you have one parameter. Okay, so this result rolls out some claims from Monte simulation, which is a very interesting result. Actually, these are my friends, so it's okay to to see they are wrong. Okay. We will require something similar for Anchor 1 SCFT later. Okay, that's why I'm mentioning this. And so how do we do Anchor 1 in the supersymmetry? Yes, but when you run the numerics, you realize it's 0. The OP is 0. Well, I mean, if you think about it, when you do Bootstrap, the OP can just run to 0 by itself. Or you allow it, but it's not necessarily there, right? Yes. Yes. Exactly the same curve. Yeah, it does the same. Actually, that's a very good question. In fact, if you think about it, that actually means this is not the most stringent bound, right? I mean, if you in actual CFTs, epsilon is non-zero. So therefore, if you this is a very low bound. The real bound should be much higher. It should be slightly higher than this one. Okay. Any more questions? Yeah, sorry. I copied from it's, you call it, 0 means neutral under any Fourier symmetry. Okay, this is the next one, which is also neutral under any symmetry. That's what the definition of epsilon is. Or you, in ON vector model, you call it phi square. Or, yeah. Yes, yes, that should be the one. Yeah. Okay, so yeah. So how do we get constraints from supersymmetry? I'm talking about n equal 1 supersymmetry. Therefore, the multiplets are very short, and because it's 3D, there's no R symmetry. Okay, then therefore there's no much about exact result that you can obtain. But indeed, you can do one thing. You assume you draw a line. Let's see. For example, I'm going to start this. Sorry, I'm going to start this theory, which W is sigma to the third. This is the Westermann model. So in that theory, the leading operator, basically you can write sigma in terms of sigma and theta bar psi and theta bar theta epsilon. So they are related to each other by supersymmetry, this sigma and epsilon. Okay, and therefore the only thing that you can do is to draw a line. The first thing you can do is to draw a line, right? Y equal to x plus 1, and then you'd have an intersection, and this gives you a lower bound for this delta sigma. Let's see. Some similar things was done in this paper, and it's based on similar results. The bootstrap fermions, and fermions are related to sigma by 1/2, so you can similarly draw a line there. But actually, they contain a little bit more, which is why it motivated us to look at this theory more carefully. Okay, so what about OPE relations, right? I mean, how can we get some conformal block? Let's first remind us what NQ2 bootstrap tells us. Actually, the superconformal block contains 4 terms, which is there are some coefficients in front of them, which are basically the OPEs, because the OPEs are related to each other, right? So, for example, this is a generic long multiplet, and the R charge equal to 0 ones are these, and these are the 4 operators that appears in the 4 blocks, basically. And you can derive conformal blocks, and you put this in your computer, and it gives you some constraints. But this cannot be possible for n equal to 1. The reason is this. For a generic long multiplet, let's see, it's where generic supermultiplet, it's very short, and it starts with something with spin G, let's see, and then there's a Q acting on it, there are 2 fermions, and there's another Q, okay? But the point is that their parity are different. If you preserve time-Rosso symmetry, they have different parity. So this means that they cannot appear together in phi-phi OPE. Suppose one appears, the other would not appear, basically. That means your superconformal block of the primaries, I'm assuming phi to be a superconformal primary, of the primaries contains only 1 term, okay? And the so-called superconformal block in the traditional sense has just 1 term, and you cannot do anything about it. There's no OP relation, so you can impose. So okay, this is what I mentioned. Yes, that's exactly my point. You don't have constraints from supersymmetry. That's basically because n equal to 1 is too small. And yeah. So let's go further. So to proceed, we have to take external operators to be not only superprimaries, but also descendants. This is what we did. And to explain this, let's see. Because, as I explained, this is the structure of the multiplets. Suppose, let's say, sigma OP contains this G with positive parity. Then epsilon sigma OP can contain the other one. You can see that these OPs are related to each other, and these are how you put in these constraints, basically. It's a very simple idea, actually. But how to get these OP relations? Okay, Junhe Park, he classified the 3-point correlators in terms of super coordinates, and there are some capital theta and capital X. this capital theta and capital X basically brings all your superconformal transformation into the first point. Okay, as you can see, under superconformal transformation, no, actually this is xi. All the superconformal transformations is bring back to the first coordinate, even though that this capital X1 contains 3 different positions coordinate. This guy is transforms only in the S01, 2 times dilatation at point 1. Okay, therefore you can construct superconformal invariants in that and write down the 3-point correlators. Basically, there are 4 different structures. Basically, there are 4 different multiplets that can appear in our theory. There are 2 bosonic ones with plus parity or minus parity, and that's the one I explained. But there's also fermions, and it starts with a fermion, and there are 2 bosons with same scaling dimension but also opposite parity. Okay, and it goes back to another fermions. And these are the 3-point function structures that gives you well, these are the 3-point functions when you write it in supercoordinates. Okay, then just to show it again, this is capital X, capital theta. This is how it looks like. What you do is basically you do a theta expansion, because for example, if O is some operator and phi is you look at this correlator and you expand it in theta, and there's one term that contains no theta, which gives you phi O plus, and there are terms which carries theta in this and this coordinates, which gives you FF and O plus, and there's these ones, and you can read out the OP relations in here. There are a few tricky things. The first thing is that this theta term, actually I'm cheating here. This F is not a superconformal primary. You have to subtract the contribution from descendants. And also this F and O's are not normalized to be 1. But that's details, so let's skip that for the moment. These are the relations we got in the end. And what do we do about it? Well, I mean, we have the bootstrap training for Eisen model, right? Which is considering sigma, and epsilon, epsilon. And now I'm telling you that these 2 OPs are related to each other. So you can just plug in, and this 2x2 matrix now contracted into a 1x1 matrix. And some of these terms are also this OP are also related to this OP, and therefore just added them together to treat them as a block. And that's what you do. Yeah, basically these are the correlator considered: sigma, sigma, epsilon, 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 sigma, epsilon, sigma, epsilon, and these ones. It gives you 5 equations. Okay. And with this, they discovered the famous Eisen island, of course. And after, as I said, after what I said, oh, this is the Eisen model island. Yeah. So I'm just saying that using this bootstrap equation, you can discover. Yeah, non-supersymmetrical island. That's the famous one. And okay, now these are our bootstrap equations. These D's and E's are the OP coefficients. Sorry, I'm using different notation, but hopefully it's clear. Is it clear? I'm just putting these OP ratios in here, and it contracted from 2x2 into 1x1, and I got some bootstrap equation looking like this. Yes, you can do. I'm going to comment on that later. Okay. Okay, it's equivalent to do that. Actually, you can write down on that for 4-point function, and with some prefactor, there's a scalar function which is in a base of super invariants, right? And then you act Casimir recurrent on top of it, and then you solve them. And then in the end, you get the component blocks. But usually what people do was to take all the theta to be 0, right? Theta 1, theta 2, theta 3, theta 4 to be 0. And in that language, what I'm saying here is that it's trivial. In that case, it's just 1 term. But here, you can similarly do that, and then take not only just the term which contains no theta, but also other terms which contains theta. Yeah. This is, I think that's this approach, yeah. And there's a tricky part, in fact. I mean, in the end, we discovered that these 5 equations are not fully independent. Okay, and we had to delete one line. I mean, later you can by counting superconformal environments, you know there are 4 independent equations, and that's the drawback of that approach, basically, because if you just do that, you don't know how many independent equations are. Okay, the targeting theory is this one, very simple theory, where there's a boson, there's a Majorana fermion, and basically coupled together. Okay, you call coupling, and also sigma to the 4th. The theory preserves time reversal symmetry, and that symmetry sigma goes to minus sigma. Okay, and when lambda 1 equal to lambda 2, the model could be written as a Western model with the potential of this form. And this theory has a property called emergent supersymmetry. Why is it emergent supersymmetry? That means you don't need to tune any parameter to reach that fixed point. And that means non-supersymmetric RG flows can naturally flow to that fixed point. Okay, so this means that the CFT spectrum must contain only one time reversal even singlet operator. Okay. You cannot have too much if basically the one I'm talking about is epsilon. So you can think about this, you build up some lattice system, maybe some material that you tune temperature and reach the fixed point, and you discover that supersymmetry is emergent, enhanced. Okay, it was argued in this paper that it can be realized on the boundary of 3 plus 1 dimensional topological superconductor, but it has been 4 years. I don't know if there's any chance of experimental realization. But again, emergent SUSY is important because you don't want to tune too much parameters when in your experiment. Okay, so let's remember that I need only one time reversal invariant scalar operators. Okay, these are earlier works based on loop calculation and summation. And if you look at the spectrum, there's indeed just one time reversal invariant operator, which is this one, and all the others are odd. Okay, this is the descendant of sigma itself. Okay, 1.59. This is the one. It's the descendant of sigma itself. Okay, that's the only one time reversal even operators. Is a yeah, exactly, perturbative calculations. Yes. That's a good question, but it's connected to I don't remember which one. It's a supersymmetric angle one supersymmetric. No, it's a supersymmetric model, but the spectrum is a tricritical isomodel. But it's not the same order. OPEs are different from tricritical. It has to have supersymmetry. Right. So yeah, you mode out some spectrums, and then there's a supersymmetric theory. Yeah. Yeah, how do we impose emergent supersymmetry? Remember, my notation is that boson, this means the primary is a boson and it's plus, okay? That means that my boson plus or multiplets all have to have scaling dimension bigger than 3, okay? That means my boson minus needs to be bigger than 2 because its descendants is time reversal invariant. So if it's bigger than 2, then its descendants is bigger than 3, then we are good. And we have to require this guy to have with G1/2, and this is a fermion primary, and its descendant has bigger than 3 means this fermion needs to be bigger than 5/2. Okay, and then this is our result. And these are, after you impose that condition, you bound the boson minus leading boson minus operators, and then you get this result. And there are some whole allowed regions, but there's a pike. That's precisely the location of that model I was talking about. Okay, and if you require the theory to contain only just 2 boson minus operators, which are less than 3, dimension is less than 3, you get a bootstrap island. You can see this bootstrap island is very small, and it's not. It's 1 digit bigger than the Eisen island, but still it's quite small, quite precise determination. Oh, okay. This I just bound the leading boson minus scalar operators, and this one I require this to contain just one boson minus operators whose dimension is less than 3. Oh, I'm zooming in this, yeah, exactly, this tip. Okay. Well, actually, I think it jumped appears, if you, this is lambda equal to 13, if you are familiar with numerics, this is pretty low. And if you do it more carefully, it jumps appears at 1. This is probably some n equal to 2 series, because which is conserve current multiplet. Let's see, n equal 2, and it has scalar whose dimension is 1, and that's probably because of that. Yeah. Okay, so this is the island, and also see David Poland and colleagues' paper. They also discovered this independently. Okay, then you can improve the numerics. We are working together now, and you can shrink the island as you move further and further. But really, I think, well, just to comment, the derivative base is probably not derivative. When we are doing numerics, we are doing derivative in z and z bar equal to 1/2 with different power of derivatives. But this is a pretty bad basis for the functional, actually. So I think one of the efforts that many people are doing, especially Dalmil and colleagues, are to choose a better basis for this thing, to improve numerics. Okay. Okay, this is simply the 2+1 dimensional CFT after Eisen model, because it contains 2 relevant scalar operators. This is the bootstrap observation, if not confirmation of the existence. Yeah. Exactly. Okay, that's a very good question. Actually, one of the things that we are really pushing numerics, why you can see why do you care about the high precision determination of critical exponents? The reason is that suppose we have 20 digits, we might be able to guess something, right? That's one of the efforts. So actually, I have a very interesting. Well, actually, nowadays we have the best known things are the Eisen model critical exponents. It's approximately pi. I think it's. I have some weird expression 1/6. F2. This is F2 is called the second Feigenbaum constant. Okay, this you might be wondering why did I get this? You can go online and search inverse symbolic calculator. You put numbers there, and it guesses for you expression. The hope is that if we push numerics much further, exactly. I mean, it's kind of a surprise. If it's I don't know, because this is n equal to 1 and there's no exact things results. I don't know if we will be a new nature constant, like the Feigenbaum constant, or just some rational world. Yes. I would say this has been tested because I have a very small island which has not disappeared yet. Right. Because yeah, if it's not like that, it should be disallowed. Right? Yeah. Yeah, actually, I think that song would be excluded. It's probably somewhere in the edge. Yeah. So I don't remember if this one is excluded, but a few more. But its song would be excluded, I think. Sure. Yeah, I didn't do that, but this is give you some impression. Actually, I don't expect that because simply I also don't expect that if you do ISA model. If you no, it will shrink to zero to where well okay. It's harder and harder to get 1 digits. The next 1 digits it probably takes at some stage it probably will take you more than thousands of derivatives. Right. No, I think okay. But this is just my guess. I think if you consider infinite derivatives, you will get a point. I think. Yeah, that's also a good point. Counter argument for that. No, but you have these are the closed set of operators that you solve your crossing equation. I think they are sure. No, but actually the 1D story, the 1D functional, extremal functional, already gives you the precise value. Yeah, these are just. I'm sorry. I'm believing it will shrink to zero because these are my impressions or intuition. Whatever. Okay. Any more questions? Okay. This is some comments. Okay, so this CFT has a Runner spinner. Time reversal symmetry is actually anomalous, and that's why you have to put it on the boundary of the 3+1 dimensional superconductor, or in the CFT in the field theory language, you have to put some topological terms in to cancel this anomaly. And yeah, okay. And the another lesson is the descendants are important, really, really important, and it's really powerful. Okay, so the island has some value, and okay, you can translate it into eta and 1 mu. Sigma prime contains superprimary with this, but its descendants is 3.882 in terms of critical exponents. Omega is this one, and you can also determine the central charge, which is roughly this. Okay, and also, okay, the other thing that we care about high precision determination is because we can use them as a point to resum the known results, like epsilon expansion, or for example, one example is this large n expansion of psi of the Fermion fields. This is one point of Grosne-Wu model. This is a lower end of that model, so you can do two-side Pedari summation to improve the estimation for other ends, other species of Fermions. So this is some result, and some values. But anyway, this is not so important. Okay, so I still have how much time back? Oh, okay. Oh, good. Precisely half an hour. Okay, now let's move on to the next topic. We are going to discuss how to include flavor symmetry in this system. So as I said, instead of considering, you just put an index on all the fields, and because remember that your field is this, because the flavor symmetry commutes with superconformal symmetry, therefore they are in the same representation of the flavor symmetry group, and the actual Bootstrap N long and complicated. It is not very illuminating to see their explicit form, but let's see one example. Let's define these so-called projectors. Basically, your 4-point function would be decomposed into projectors times some lambda OPEs in this I representation. There's a summation over the representation that appears in, let's say, vector times vector representation. And there's another summation in the operators in this spectrum. And there's OPE squared and the block. But on the right-hand side, there's a I and K flip. Okay, these are the equations. And do some manipulation, it becomes something like this. And it just depends on this M, R, and R prime. These are the things we saw yesterday in the ON bootstrap. Yeah, so anyway, your bootstrap equation just depends on this M, and you know this M, and you would know how to write down the bootstrap equation. And a few days ago, there was a release version for auto boot by Go and Tachikawa, and probably it's easier to use that one. We will further require that our flavor symmetry group to contain a fully symmetrical invariant tensor, which is called DIJK. Let's denote them. Or in other words, we need the product of two vector representation to contain the vector representation itself. Okay. So this reason for this choice is related to a trick that we are using, which will be explained shortly. Let's just look at the result for S4. S4 is a permutation group for Potts model. No, false state Potts model. The curve looks like this. The horizontal axis is our phi I, which is the superconformal field in our vector representation. The vertical axis is the leading B plus scalar in N channel. This is parity odd. Remember, phi itself is parity even, and this guy is parity odd. In free theory, this operator would be this guy. Okay, DIJK phi K. Okay, the jump corresponds to Western minimum model with the superpotential term of this form. Why do I believe that? This is because equivalent motion tells us at the Western minimum model point, this guy becomes a descendant of this guy. Okay, equivalent motion, just from equivalent motion you saw it. And since conformal bootstrap only gives us scaling dimension of the superprimaries, we observe this jump. So I'm basically saying that initially these curves are not too much different from generalized free theory. There may be some interacting theory there, but their spectrum is not very different from generalized free theory. But as you meet the Western minimum model point, that guy got eaten by the phi itself, and you have to get a much higher bound. That's a feature for Western minimum model. Okay. So. D is the invariant tensor that's assumed to be existing. SIJK, no. Well, I just know that S4 has such an invariant tensor. Okay. Yeah. So you do differentiation with phi, you get this. This is okay. So I'm claiming that this is the location of Western model. And to further support this identification, let's see a spectrum of a known theory. Let's pick the group to be S3 instead of S4. And you can do a similar plot. And the jump appears precisely at 0.666, okay, which is a scaling dimension of Inco 2 theory with Western with superpotential of this. Okay. And so what I'm just seeing here is that Inco 2, this Western minimum model, in terms of Inco 1 language, this R symmetry gets broken into S3, but you have another Inco 1 supersymmetry. Okay. Okay, Inco 2 R theory has R symmetry. The superpotential needs to have R charge 2, hence the superfield needs to have R charge 2 over 3. And therefore, at a critical point, superconformal symmetry fixes its dimension to be 2 over 3. That's precisely the value we observed in numeric's. So that our identification is probably correct. If we fix delta phi to be 2 over 3, then we can bound this guy leading and this guy. Okay, you get a curve like this, and you got a notation. You got this guy is approximately 4.5, and this phi square. Sorry, it should be capital phi square is 1.9. Okay, and this is, you can compare with the known result from Bootstrap, and you get similar values. And we are confident that this identification is correct. And so our identification is probably correct. Okay, we can do further. We can change n, right? And then you have a plot. What I'm doing here is that I'm drawing a straight line here. Okay, then I'm compressing it into one dimension along this delta equal to 3. So I'm just basically requiring this guy dimension to be bigger than 3. Okay, and then I have some 1D problem, which there's a disallowed region in small delta phi and allowed region in bigger delta phi. Okay, and I'm plotting it. This is a plot in terms of 1 over n. And okay, so as I said, in small delta phi is disallowed, bigger delta phi is allowed. First of all, these are the locations of the jump, okay? and you can compare it with the epsilon expansion calculation. Sorry, and this red curve is the epsilon expansion calculation. This region is because I require the superpotential to be dimension bigger than 2. If you add that condition in your bootstrap, you actually can exclude a little bit more regions, and you have a lower and upper bound for large enough ends. Okay. The reason that we require superpotential to be bigger than 2 is because it's an infrared theory, right? In terms of Lagrangian or whatever. Okay, so this is Sn, and there's one interesting thing is that at large n, delta phi approaches the Eisen model value. The epsilon expansion series can also be shown to approach the known value series for the Eisen. So basically what I'm saying is that this post model, as you increase n, go to large enough n, it decouples. It becomes large and factorization, it decouples. And then, it decouples into, but instead of decoupling into a free theory like one vector model, it decouples into some interacting theory. Each piece is some interacting series. Similar things was observed if you do this bootstrap, non-supersymmetric bootstrap. As you see, you will observe some kinks, and the kinks approach this Eisen model value. I forgot to put citations there. Well, since this is this is very free discussion, I don't know if it's possible to get some the one-word corrections in terms of the Eisen model OPEs. Of course we don't, for free theory we can solve everything. We basically know everything, but this decouples into a interacting series, many species of Eisen model, and probably the Eisen OPE spectrum can give us some information about this large n, and we can compare with the numerics, hopefully. No, that's what I'm saying here. I mean, if you, I don't know analytically, but the only evidence is this. If you do epsilon expansion, and you get a series, right? You strictly take n to be infinity, and you find that series is the same as Eisen model, epsilon expansion series. Please? That's a very good question. No, I haven't. Right. Yes. That's going to be one of the interesting things to look on, maybe. Yeah. This is a question mark because I don't know whether this is possible or not. This is SUN. Similarly, you can do SUN. This is allowed regions, and this is similarly the epsilon expansion result, and you can compare them with. Okay, so why do we care about these Western models? The SU3 invariant models is very interesting. So if you consider 3D QED-like series with 2 chiral multiplets and with charge 1, the explicit symmetry of the theory is SU2 flavor times U1, which is vortex topological symmetry, and the U1R symmetry. Using geometric features of 3D correspondence, it was pointed out by these groups that in the IR it has an enhancement into SU3. Okay, the flavor symmetry, these two enhance into SU3. And later it was also proposed that theory has a due description in terms of encode 1 Western window models with a superpotential term which is W equal to this guy. Okay, this D would be the invariant tensor of SU3 group. Okay. And so in the infrared, supersymmetry enhancement happens. But for the duality to work, it's necessary that this Western window model, delta phi, gets strongly renormalized and becomes delta equal to 1. This is because in the duality, phi is due to the encode 2 superconformal primary in the conserved current multiplet. So because of encode 2 supersymmetry, it fixes its dimension to be 1. However, as I have showed you, our result, our encode 3 kink was not really at 1. It's around encode 0.8. Okay, so we could never fully rule out the possibility that the jump observed in numerics correspond to some new unknown CFT rather Westman model. But from my argument about this decoupling of DIJK, phi J, phi K, I think it's pretty believable that this should be identified as a Westman model. And so, yeah. Also, I noticed that the result agreed pretty well with this two-loop results in extension. And if you put this guy at lambda equal 21 bound, and you can analyze this operator's dimension, you get a which is 2.8, and the epsilon extension tells you this is 2.35. So the match. Okay, so the thing here, the upshot here is that our result match with loop calculation, but doesn't match with the expectation of the duality. So I don't know why. Right. But you can. Yeah, exactly. So but this is probably still okay because you can see the series are this over this guy is less than 1. Yeah, that's also actually that's a very good question. That's also one of the reasons we care about high precision determination of critical exponents, because even in Eisen model, I think if you now I think the known result are 7 loops, but I don't think the going from 6 to 7 loops when you do resummation would improve the error correction. Another example was recent some 5 loop results for cubic model, and also so indeed, I mean, I think probably people should rethink about resurgent and how to better extracting information from epsilon expansion. But back to us, I'm just saying this is the result. But as I said, I have many evidence. This works. This Enkel 2 example works precisely at 2 or 3, and other spectrum also works pretty well with Bootstrap result. So I think our trick is probably correct. But yeah, it's a little bit troubling that it doesn't match the duality. But I don't know, the duality, this Enkel 1 duality, it's not, there's nothing you can calculate from the Enkel 1 side. So there's no non-perturbative comparison in that case. So I don't know. So yeah. There's another family. Remember, I required my flavor symmetry to contain something called DIJK. It's called F4 family of flavor symmetry groups. And just let me remind you what F4 family is. It contains the F4 group, Lie group F4, SO3 with symmetric traceless rank 2 tensor, SU3 adjoint, and also SP6 with anti-symmetric traceless rank 2 tensor. You might also see that this, as Fernando already mentioned, this guy, these are the epsilon expansion series result. I didn't resum it because this is not enough, so therefore resummation does not improve a lot. But as you can see, the leading one, this one, the convergence seems to be still okay. But if you look at this one, it's pretty bad. So therefore, it's off match. So, but probably this, I believe numerics is still correct. This value is still correct. Okay. Okay, let's. The so-called F4 family is the so-called Bird-track compactification. It basically requires a invariant tensor to satisfy some relations. Okay. Let me not talk about that in detail. Okay, I'm doing very fast. You have 15 minutes. Okay, let's see conclusions. Conclusion 1 is descendants are important. Okay. Conclusion 2 is the Enkel 1 duality might be tricky. Okay. These are our conclusions. Can we do like on Bootstrap? Okay, because this island is very small. Remember, there was a work by Devin Simon-Duffin did the Eisen model. Because the island is small, so can extract spectrums of higher generalized free theory-like spectrums. and compare with the numeric's. Because this island is also very small, we can do that also, we believe. And up to now, we have solved the OPE coefficients for n equal to 1 generalized free theory, okay, or just a free figure in ADS4. This was done by combining the known OPE coefficients for non-SUSY generalized free theory, and also with our n equal to 1 bootstrap equations. You can solve if I don't know if it's interesting, but we are pushing this direction also. Try to get the Lycos, please. Exactly. Yes. I'm going to comment on that and then see if you can, if you still have more questions about that. Okay. Can we add fermions? Remember, we just considered the phi, 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 f, 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 f. But can we add fermions? It turns out, by counting superconformal environments, assuming T time reversal environments, it can be shown this is not necessary. Okay, so we are lucky. Boson scalars are good enough in this simplest set. But as I said, you have to assume time reversal environments, and if you consider time reversal breaking CFTs like Chen-Simmons series, you have to you will have more bootstrap equations, and therefore you have to consider fermions for completeness. Okay, what about other bigger supersymmetries? Right, descendants are important, and it's very tedious to derive the full set of Poisson equations. Probably we need to find a good way to do that. Okay, so can we do other n equal to 1 Western-Minnow models? This is your thing, what you said. See ON symmetry. Okay, in this paper, there was mentioned we care about n equal to 1 Western-Minnow is that they are related to various n equal to 1 dualities. One of them is this one. This W equal to H P dagger P. Okay, H is an O2 singlet and P is a complex scalar. The theory has an O2 symmetry. But on the QED side, this theory contains the Chen-Simmons-like terms. Okay, so basically what's happening in this proposal is that on the QED side, time reversal symmetry is emergent. Okay, so this means that for the duality to work, the time reversal symmetry breaking operator H square. Okay, remember I'm talking about superpotential terms. So H square is actually time reversal symmetry breaking. H cube is preserving time reversal symmetry. Okay, so this term needs to be irrelevant, means that its dimension needs to be bigger than 2, because otherwise on the QED side the flu would just go away from the fixed point. Okay, yeah, that's actually initially how why we started to do this, and yes, learning from our previous experiments, we noticed that the most straightforward way is probably to use the trick that HPI becomes the superconformal descendant of PI, right? Because that's where this jump appears. Okay, that means we have to be able to access vector representations of ON group. Okay. Yes, in other words, we should bound the leading B plus scalar operator that transforms in the vector representation of ON. Yeah, so to do this, we cannot just consider PI, PJ, PKPL, because this guy does not contain vector representation. H itself does not, but we have to consider mixed operator bootstraps. And then in this H times P, it contains that representation. So we hope to report about this later. So the plan is to sorry. The plan is to do this and see if we can find a jump similar to that, and then to use extremal functional method or whatever to measure that H square operator's dimension to see whether it's bigger than 2 or smaller than 2. Okay, this is what we are doing now. I still got 10 minutes. I was going to stop here, but let me see a little bit more about this countings of whether we should include fermions. And remember I said there are some super coordinates, capital X and capital theta, Using them, we can count the superconformal invariants in encode 1 superconformal field theory. And turns out, anyway, turns out there are these are the ones, and these terms destroys time reversal symmetry, and these terms preserves time reversal symmetry. Okay, if you write an ansatz for your 4-point function with this, and therefore simply from this counting you can see that they are, if you just keep the ones that preserve time reversal, it will give you four equations just. Okay, similar stuff was done in this paper. Okay, that's it.